Hey, this is Craig Garczynski, and welcome back to the Yorkshire Dales in England. Today I'm in a county called Cumbria, which is right next to Yorkshire, and Cumbria is home of this home here. I don't know if you can read it on the screen, but it says Faraday Cottage. This home was where Michael Faraday's father, James Faraday, was a blacksmith. When I say Michael Faraday, for me at this point in my electrical career, I can say Michael Faraday, and it's a guy that I've referenced for many years. But for some of you, you might think Michael Faraday. I don't know that name. Last week, I gave a reference of James Watt, and Watt is a household term. You don't even have to be an electrician to say watt, to use a 100-watt light bulb, or to pay your electric bill that's in. Your electric bill is in kWh, or kilowatts per hour. Michael Faraday is one of those guys that you might think, was he a football player? Or, oh, no. He was, that's right, he was in that movie with George Clooney. Some would say he's the father of electricity, so that's a pretty big deal. In 1791, the year that Michael was born, they moved from this cottage and moved down to the London area, where then Michael Faraday was known for doing a lot of his discoveries and inventions and contributions to the electrical world. One of the greatest contributions that he made that directly impacts us as electricians and everybody as electrical consumers is his contributions to the electric motor and the electric generator and his discoveries with electromagnetic induction. Hey, welcome back again, but this time to my home office. The weather turned in Cumbria. It was supposed to be 70 and sunny and a perfect day to be outside, but it didn't turn out to be that way. So the remainder of this lesson of alternating current will be here from my home office. Let's talk about the historical timeline of alternating current, starting with what I believe was the catalyst, Michael Faraday's discovery of electromagnetic induction in 1831, which then introduces my next guest, who's one of my favorites to talk about, Nikola Tesla. Tesla was born in 1856 in Croatia, and to say that Tesla was brilliant is an understatement.
Let me put it this way. Have you ever heard of Plato, Aristotle, Socrates?
Yes.
Morons.
It's like he was playing a different game than people that were around him. I grew up a Detroit Lions fan, and I used to say that about Barry Sanders. Like, is that guy out there? Is he playing by the same rules that everybody else is? He's just that much better.
It's just a matter of time before everyone on this team is going to be heard from. You think you got him tackled? No. That's by keeping your feet going and making Sanders move. Some of those moves, there's only one guy in this game that makes, and you just saw that guy.
That's the kind of mind that Nikola Tesla had. He was so brilliant, such a visionary, that he could see into the future and he could see where everything needed to be. Not just where we were right now, but where everything needed to get to, which sometimes caused some friction. The Second Industrial Revolution began in 1870, and the U.S. was center stage for industry and for innovation. And Tesla moved to America in 1884 to be a part of this movement and immediately started working for Thomas Edison. Everything at that point was moving forward with direct current. And Thomas Edison had one of the smartest guys on the planet working for him. All things were going in the movement of DC with investment and electrical infrastructure. And yet, Tesla knew that there was a flaw with DC, is that DC can't be transformed. And what that means is that it's not good for transmission and distribution. There was friction that developed between those two and a great rivalry. Some of it is factual, and you can look it up on Google, and other parts of it are opinion on how those two clashed against each other. Edison often villainized, and Tesla oftentimes is almost like a superhero flying around with a cape.
You know what? You like to think that you're just like Tesla, but the truth is, you're exactly like Edison.
You take that back. No? He's right. You are a bully, a credit hog, and a self-promoter. And if anyone around here is like Tesla, it's us.
Yeah.
Even though there was a friction and a misunderstanding that was developing between those two, Tesla took advantage of this time and perfected a number of pieces of equipment that Edison was working on. In fact, Tesla has almost 300 patents in the electrical industry, and a good amount of them were patented during this time that he was working for Edison. Those two then parted ways, and Edison remained in this way with his company General Electric, financed by a guy named J. Pierpont Morgan, or J.P. Morgan. My wife and I own a home in Denver, and our mortgage is through Chase Bank, and on our mortgage statement it says J.P. Morgan and Chase Bank. Tesla went this way with alternating current and had somebody that believed in his system named George Westinghouse. Tesla and Westinghouse then went on to build the world's first alternating current power generation station, known as the Ames Hydroelectric Power Plant in Ophir, Colorado, near Ouray. Tesla primarily worked in the US, in New York, and in Colorado during this time. Then those two came together in a battle known as the War of the Currents in 1893. It was Tesla versus Edison. It was alternating current versus direct current for the way of industry and the way of the future. So many things were happening at that moment in time that were all being highlighted. The fact that it was in Chicago, which had experienced a devastating fire in 1871 that wiped out almost the entire city, and showing the resilience and the spirit of that community. It was world innovation all coming together. A number of countries that were represented at the World's Fair, including Norway, which built a Viking ship and sailed across the ocean to then dock into Chicago. A number of other items were highlighted during that time that we know today, like the zipper. The Ferris wheel was first introduced during this fair. And Pabst Blue Ribbon. Before this fair, it was called Pabst Best Select, which then won the blue ribbon at this fair. So if you're ever at a bar or a pub and you order a PBR, it's called the blue ribbon because of this fair. Tesla and Westinghouse won the bid to light up the fairgrounds during this fair. And as you notice in your Delmar book, it says that AC was chosen over DC because it can be transformed. And because it can be transformed, it's cheaper for the electrical infrastructure. Because it's cheaper, it was able to be awarded the contract during this fair. Can you imagine being in the public and being at the World's Fair and watching it being illuminated with electric lighting for the first time? It's one of those things that I think that I've certainly grown numb to, even though I still enjoy it. Places like Las Vegas or any big city that's got electrical lighting throughout the whole area. Can you imagine seeing that for the first time on a grand scale? So not only did the public see it on a grand scale, but the investors saw it and they said, wow, this is not only spectacular, but it's cheaper. It's cheaper than the DC system, so let's invest everything that we have into this alternating current system for the way of the future. And that's when Tesla and Westinghouse got the contract to power up the Niagara Falls hydroelectric plant, which then powered up New York City. It began what some people would call the electrical age, starting in 1896. And then if you have your National Electric Code in front of you, open that up and look at the front page. And if you have your 2020 NEC, it's going to read that this is the 55th edition of the National Electric Code, which supersedes all previous editions. And look at the dates of the ones directly below that, and it says that it began in 1897. So we can see the advancements of the electrical age into the National Electric Code and into the documents that we're using today. As I close out this portion of the historical timeline with alternating current, I'd like to point out a few things in my office. It was said that if you were to be in Albert Einstein's office and in his study, he had a picture of Michael Faraday on the back wall that he used for inspiration. Some of the things that I like to use for inspiration are historical. This piece right here is the picture of the Hoover Dam intake towers, and this is right before the river was flooded to become Lake Mead. And then this picture here is one of my favorites. This one is also during the Great Depression, and ironically, this is just coincidental. I just happened to look up a fact on this picture, is that this picture's anniversary is today. It was taken on September 20th, 1932 during the Great Depression. And so I have those items in my office as sort of my inspiration, an electrical inspiration, along with this Nikola Tesla silver coin that was created by the Serbian government. They did a series starting in 2018, and this one is his let's see if I can get it on there. This is his contributions to alternating current. If you can see that, alternating current, lighting the world, 2018. They then created a couple of coins in 2019 for his contributions to remote control, and 2020 to his contributions and innovations with the X-ray. So I've spent some time now on the who and the when of alternating current. Let's look at the what part of alternating current. The two greatest pieces, I think, in understanding alternating current are having an understanding of Faraday's law and Fleming's rule. Faraday's law says that the amount of voltage that's induced into a conductor is proportional to four things. And those things are the strength of the magnetic field, and then the angle, the speed, and the length of the conductor passing through the magnetic field. And Fleming's rule, which is named after an English scientist named John Fleming, who's from an area not too far from here in Lancaster, Lancashire. He's got a right hand and a left hand rule. One is for generators and one is for motors, inversely. His rule says that if you, the thumb is typically known as the thrust of the conductor. This finger is, the forefinger is the magnetic lines of flux, and then the middle finger would be the motion of current within that conductor. Notice that the motion of the conductor is going this way if I'm thrusting up and the magnetic lines of flux are pointing this way. But when I spin it and I thrust in the opposite direction, the motion of the electrons within that conductor are going the opposite way. And that's the fundamental principle behind what's going on with alternating current. Now let's piece together some of these things with Faraday's law and Fleming's law and put them into these two diagrams that I have. This diagram is of a unit circle representing the turbine in an AC alternator with north and south magnetic poles and magnetic lines of flux shown by these blue lines. And in this diagram here is a graph of what we're going to draw as our sine wave. And the unit circle has very specific characteristics. It's got a radius of 1. It works in a counterclockwise direction with quadrants 1, 2, 3, and 4. And showing 90 degrees, 180 degrees, 270 degrees, and then back here to our starting point, which is either 0 or 360 degrees. When I have a conductor inside of this unit circle, inside of our AC alternator, right now, if I'm looking at Faraday's law, which says that the amount of voltage that's induced into this conductor is proportional to the angle at which it's cutting the magnetic lines of flux. Right now, in theory, I'm not cutting any magnetic lines of flux. I am parallel with them. I'm not perpendicular to any of these magnetic lines of flux. So right now, I have 0 voltage induced into this conductor, which is represented by this point right here on my graph, 0. And then as I turn in a counterclockwise direction and go maybe to 30 degrees, if you on your calculator do 30 degrees and then push the sine function on your trigonometric calculator, you're going to get an answer of 0.5. Your sine function is going to be anywhere between 0 and +1 and 0 and -1. So 30 degrees sine is going to give you a 0.5 plot point, which then I put over here on my graph. And then I go to 45 degrees, and if you do 45 sine, you're going to get 0.707, which is shown right here. And then if I go to 60 degrees sine is going to give me 0.866, which is here. And then if I go to 90 degrees, I'm cutting the maximum amount of lines of flux, and I'm going to get a maximum voltage induced into this conductor. Sine of 90 degrees is 1, which is shown here by this plot point here. And then as I continue around the circle, I'm going to get plot points that are positive until I start getting into this section of the unit circle. So far, we are positive values. But notice, as you do this next one, coming around in this direction, if you do 180 degrees and then maybe add 30 degrees, so you do maybe 210 degrees and then do the sine of that, you're going to get a negative 0.5, which is our plot point here. And then we continue on in this direction. All this area of the unit circles are going to give us negative values. So then we have our plot points here that we can connect and show what we know as the sine wave. The sine is the opposite side, which is this O that I've got written there, divided by the hypotenuse, which is the H here. So this triangle that's formed within here, the sine function is this side divided by this side, which is giving us our plot point, which intersects with this plot point on this vertical axis known as the y-axis, which is a representation of this y-axis and where it falls vertically on this sine wave. If you're trying to wrap your head around alternating current, you're going to say, okay, great. If I take all of these values and plus these values and I get an average of this entire sine wave, what's funny is that the average is 0. So some people might have been looking at Tesla like, okay, I know that you're a smart guy, but the average of your sine wave is 0. But it doesn't work like that. We use a term known as root mean square to get our average of this. And the root mean square is essentially eliminating negative values, because here we have all positive values and here we have all negative values. Not to be confused with positive or negative like we know it. There's a major difference between $20 and a negative $20. There's a huge difference. In this instance, negative just simply means direction of force or flow. So that's that way, and this is this way as a representation of John Fleming's left hand and right hand rules. So negative and positive just mean direction of force and or flow. We're going to use something called the root mean squared, or RMS, which also means the square root of the mean squared. If I have a positive 2 and I square it, I'm at 4, and I take the square root of that, I'm at 2. If I take a negative 2 and I square it, I'm at positive 4. And if I take the square root of that, I'm at a positive 2. So I've gotten rid of the negative. So the average of our sine wave here, or the type of average, is known as the RMS, which is noticed right here on this line known as 0.707. That's what your meter is doing out in the field when you're taking an RMS value. And this is going to tie in with the speed part of Faraday's law that says that the speed of the conductor passing through the magnetic field is proportional to the amount of voltage induced into that conductor. In here we have this, which is called one alternation, and this second alternation then make up one cycle. And the amount of cycles that repeat itself in 1 second is known as frequency, and that's labeled in hertz. And hertz is named after a German physicist named Heinrich Hertz. So let's translate that to some generator language. In the US, at 60 hertz. That means that that generator is spinning at 3,600 revolutions per minute. 3,600 RPM at 2 poles per phase gives us 60 hertz, or 60 cycles a second. The last piece we'll look at today is the part of Faraday's law that says that the length of the conductor passing through the magnetic field is proportional to the voltage induced into that conductor. Now I convert that to transformer language, which has to do with number of turns and turns ratio. If I have a step-down transformer with a turns ratio of 2 to 1, that means that the length of the conductor in the primary is twice as long as the length of the conductor in the secondary coil, and that's going to be shown in the output voltage of the transformer. I hope that my narrative on Faraday and Fleming and Tesla was good for your overall understanding of alternating current. And remember that alternating current was chosen over direct current for transmission and distribution. It's not superior overall to DC. We still see a number of DC components in the electrical world today. In fact, that's how the band name AC/DC got its name. When they were forming in the early 70s, Angus and Malcolm Young, their sister Margaret, noticed an appliance, sewing machine, that said AC/DC on the machine, meaning that it was a universal motor that could operate off of either AC or DC. She told her brothers, and they thought it was the coolest thing ever. They were like, yeah, like most people do when they're talking about AC, DC. And that's how they got their band name. They thought it was a great marketing and great representation of the energy of their band. Bye for now, and thanks for taking the time to learn with me today. And hopefully the next time that I see you will be on a Zoom Live where we can have a question and answer session. See you then.